Welcome back, everyone. Today marks the continuation of our thrilling IPv6 journey. In our previous installment, we delved into how IPv6 devices find each other, as well as how they obtain IP addresses and find routers on the same network segment. In this episode, we're diving deeper into fascinating topics of dual stack configuration, IPv6 DNS, subnetting strategies, and the ingenious DHCP prefix delegation method designed to seamlessly distribute vast address pools to our home customers. My name is Philip. Let's get started. As we practically run out of IPv4 addresses, the world needs to switch to IPv6. However, this won't happen overnight. The transition from IPv4 to IPv6 is ongoing. Not all networks or devices have fully adopted IPv6 yet. It all started back in 2012 when IPv6 was launched globally, and since then, those two protocols, that is IPv4 and IPv6, need to live together. The question is, how is that possible? There's where dual stack comes into play. It enables devices to operate on networks that use either IPv4 or IPv6 protocols. Basically, you are connected to the same physical wire, but have both IPv4 and IPv6 addresses assigned. IPv4 frames running on Ethernet have Ether type set to 0800 in hex, and IPv6 frames have Ether type set to 86DD. When communicating with other devices or systems, your node can choose the appropriate protocol stack depending on the situation. Important thing to mention is that an IPv4 only system cannot talk directly to an IPv6 only system and vice versa. I will go to node 2 and disable IPv6 completely, making it an IPv4 only capable system. If we try reaching IPv6 host, it will fail. We don't have an IPv6 address nor IPv6 routes available, although going via IPv4 works. However, if we go to a node that is dual stack, we can reach the other dual stack server both via IPv4 and IPv6. Just to sum up, a dual stack machine gives you the flexibility to connect to other IPv4 and IPv6 devices. No worries if a server isn't ready for IPv6 yet, you can still access it through IPv4. This approach enables a smooth transition to IPv6 without disrupting existing connections that rely on IPv4. Both protocols operate concurrently on routers, switchers, and hosts. Legacy applications and devices continue to function seamlessly without modification since they can still utilize IPv4. Mind that this is just a temporary state. The ultimate goal is to fully transition to IPv6 and completely decommission IPv4. The question is, how can we know if the remote host is IPv6 capable? Here's where the DNS comes into play. When a device wants to access a website, it will first consult the DNS to get the site's IP address. A DNS server can hold various types of entries, most important being an A record that holds IPv4 address and AAA record that holds IPv6 address. Let's ask for an IPv4 address of google.com. To do that, we'll run host, that's the command used to get the IP, then -t, as we are asking for a specific record type, and then A for IPv4 address, and finally let's provide the domain name. Okay, we got the IPv4 address for google.com. Let's see if google.com also has an IPv6 address. This time I will ask for AAA record in the DNS. Yes, Google also has an IPv6 address. If a domain is not IPv6 enabled, like for example Amazon.com, it will not return an IPv6 record. It will only give you an IPv4 record. If we don't specify the record type, it will ask for both IPv4 and IPv6 address. Let's ask for Google.com that we know supports both protocols. If DNS returns both IPv4 and IPv6 addresses, it's up to the web browser or any other application for that matter to pick whether to go with IPv4 or via IPv6. Usually web browsers prefer IPv6 or use a mechanism called happy eyeballs, where the device attempts to initiate connection simultaneously using both IPv4 and IPv6 addresses received from the DNS response. Whichever connection is established first is chosen for communication. This prioritizes faster connections regardless of the protocol version. Mind that the DNS record type has nothing to do with the protocol you are accessing the DNS with. For example, I can ask DNS using IPv4 protocol for an AAA record that's IPv6 address. Let's go to our IPv4 only server and do that. Of course, there is no point in asking for an IPv6 address on an IPv4 only capable device, as you won't be able to use it anyway. I'm just trying to prove a point. The query also works the other way around. I can ask a DNS server via IPv6 protocol for IPv4 address. In summary, the DNS is crucial for smooth and user-friendly transition from IPv4 to IPv6. Users continue to interact with familiar domain names, and the DNS takes care of translating those names to appropriate IP addresses, either IPv4 or IPv6, depending on the device and network capabilities. Another thing that differs IPv4 from IPv6 is address allocation and methods to distribute those addresses to end devices. Of course, we are talking about residential clients. Let's imagine a very simple scenario where we have an internet service provider that has 203.0.113/24 IPv4 address range. That ISP provides a service to two clients, Home1 and Home2. Home1 has 113.2 public IP address, Home2 has 113.3 public IP address. Every home has multiple devices that need internet access, and we have only a single public IP. What we can do is share that public IP among all internal devices. For that to happen, we need to create a private network from the RFC 1918 range. Let's say 192.168.2/24 for Home1 and 192.168.3/24 for Home2. This will allow us to have over 200 devices inside our home network, each having its own private IP. As the private IPs are not routable over the internet, whenever an internal device wants to talk to the external world, it will send the traffic to the router. That in turn will perform network address translation, basically swapping the source IP address of the client with its own public IP so that both addresses, source and destination, are public. Then the traffic can go out to the ISP and further to the internet. If we look at how the IPv4 addresses are assigned, for the internal network it's usually through DHCP, and for external network it's usually through PPPoE. Just to sum up, individual home users usually have only a single public IPv4 address, and devices on the internal network have to use network address translation to reach the internet. Before we get into IPv6 home network design, let's first talk briefly about IPv6 subnet allocation. The IPv6 address is 128-bit long. ISPs typically get a /32 prefix for IPv6 allocation from the regional internet registry. This means that the first 32-bit are static, assigned to the ISP. It also means that the remaining 96 bits are for ISP use. They can divide them as they please. Usually the ISP will assign a /48 or /56 to the client. Let's see how that looks. For /56 assignment, the ISP will use 24 bits to identify the customer. So the first 32-bit is static, as it identifies the ISP. Following 24 bits identify the client. Each client will have a different subnet. The remaining 72 bits are for the client to use them as they please. Because we need /64 for the stateless auto-configuration to work, we are left with 8 bits to subnet our home network. In other words, we can create 256 subnets, each with /64 in size. So you can create 256 VLANs with 18 quintillion addresses each. I had to Google up the number. If the ISP assigns /48 prefix to the client, then the number of subnets will increase to 65,000. Important thing to notice is that ISP will not assign a subnet smaller than /64, as /64 is required for the stateless auto-configuration to work. There is yet another key IPv6 feature called prefix delegation. Let's see how that works. Our ISP has a very large pool of IP addresses, usually a /32. To automate the process of assigning network prefixes to subscriber networks, the ISP is running a DHCPv6 server with prefix delegation. Our home router acts as a DHCPv6 client. It will request a new IPv6 prefix by sending a DHCPv6 prefix delegation request to the server. Server will assign a portion of its configured IPv6 address space to the client router. This assigned prefix becomes the delegated prefix for the client's network. In our example, ISP delegated 1234:56/56 prefix to the client to use. Mind that we've not received a single IP from the DHCP server. We did receive a prefix, a pool of addresses. So basically, we did receive 256 networks, each /64 in size. Now we can assign one of those pools to our internal interface. Then we enable stateless auto-configuration on that interface, so all devices on the internal network will get the address via Slack. If we have more than one internal interface, or if we have multiple VLANs, we can assign another /64 to that interface and configure that interface to send router advertisements, so devices on that VLAN will configure the addresses via stateless auto-configuration. What about the external interface? We did receive /56 prefix, but we still don't have a unicast address there. We can request another /64 prefix for that interface. Few observations. On the internal network, we no longer have a DHCP server. IP addresses for internal devices are assigned with stateless auto-configuration. Another thing to note is that every device on our internal network has a global unicast address, so it's directly reachable from the internet. Network address translation is no longer needed to get to the internet. Let's see how that looks in practice. There are multiple ways to set up a DHCPv6 client with prefix delegation, but I will use systemd as it has a DHCPv6 client with prefix delegation support built in, as well as router advertisements functionality for Slack. Only issue with that approach is that it needs to be a fairly recent version of systemd. I'm using systemd version 252. We need at least version 250. Our router has two network interfaces, one pointing towards the internal network, that's our LAN interface, and other pointing towards the DHCPv6 server with prefix delegation, that's our WAN interface. At the moment, we don't have any IPv6 configuration on those interfaces. Systemd stores the network configuration in the etc systemd network folder. Let's open WAN interface configuration. There's only a static IPv4 address and static IPv4 default gateway. IPv6 accept router advertisement set to no indicates we don't want stateless address auto-configuration on the interface, as we'll want to assign an IP from a pool that we got from DHCP. First thing first, we need to enable the DHCPv6 client by setting the DHCP option to IPv6. Basically, we want only a DHCP client for IPv6 and not IPv4. For the DHCPv6 client to work, we need to set without array parameter to solicit. By default, DHCP client will start only if received a router advertisement message with stateful address configuration set to yes. Otherwise, the DHCP client will not start. It will wait for router advertisement. If we set it to solicit, the DHCP client will start without the advertisement. This is what we want. I will restart the systemd network to reload the configuration. If we look at our routing table, we have a /56 catch-all route. Okay, so we've enabled DHCPv6 client on our external interface and got a prefix. Let's now open the internal interface configuration. First, let's set the DHCP prefix delegation option to yes. What it will do is assign a prefix to this interface. Prefix that was obtained via another interface. That's what we want. One interface did receive a /56 prefix, and we want to get /64 from that pool so it can be assigned to this interface. Okay, let's reload our configuration. We see that our internal interface has now an IPv6 address assigned from /64 pool. Our routing table is showing that particular /64 on the LAN interface. Next thing we need to do is enable router advertisement on the internal interface so other devices on the link can use this router. Let me open the LAN interface configuration and set IPv6 send router advertisement to yes. Let me reload the configuration. Now let's switch to the server on the internal network and check if it got the IP via stateless auto-configuration. Here you go. There's the global unicast address. If we look at the routing table, there's the /64 prefix that was obtained via router advertisement. And here's the default gateway. However, our internet access won't work just yet, as our external interface does not have a global unicast address. Let's get another /64 prefix from the /56 pool we got. I will open our external network configuration and request a prefix by adding DHCP prefix delegation option. Now, I will reload the configuration and check the IPv6 address. Do you see that? We have an IP assigned and it belongs to a different /64. We can confirm that by looking at the routing table. Yep, we see two /64s. Only thing that is missing is the default gateway. Unfortunately, I don't see an option in systemd to set the default route to DHCP server. So let's get the gateway via Slack. Let me open the WAN interface configuration and enable accepting router advertisements. I want only the default gateway. I don't want the prefix. Let's reload the configuration. Okay, the default route is there. Let's go to our internal server and check the connection. Works. Alright everyone, that's all we have time for today on dual stack configuration, IPv6 DNS, subnetting strategies, and DHCP prefix delegation. Next time we'll be diving into the world of IPv6 firewalls, privacy extensions, and setting up an IPv6 tunnel broker. So buckle up and get ready to unlock even more of IPv6 potential. As always, if you have any questions or comments, leave them down below and let's get a conversation going. Don't forget to like the video and subscribe to the channel for more tech adventures.